it's interesting to have a different kind of clocks, one that is not purely electromagnetic, relying on the strong forces inside the nucleus, and we may use it to see if the established laws of physics in the standard model are also valid or if we find some deviations.
So why a nuclear clock?
Yeah, that's an idea that came up because we were working on atomic clocks with laser-cooled and trapped atoms, and we saw some, early 2000s, we saw some limitations. And at the time, we were unsure how to circumvent it. It was like there would be some subtle systematic effect that would still influence the frequency of the atomic transition. And then we learned that there was a very low-energy nuclear transition in the range, maybe accessible with lasers. And when we looked at it in detail, we noticed that we could solve these problems that we had seen with the other atomic clocks, and it would really offer a number of advantages, we noticed, and that got us started into that field.
So what were the advantages that you noticed?
It's mainly so the nucleus, the charges in the nucleus are so much more tightly bound than the valence electron in the shell, and so they are much more inert to external perturbations like collisions, for example, or also the influence of electric fields, of external electric fields. And that's what we like for the clock. You would like the frequency to be independent of external conditions. The clock should always run at the same frequency, no matter what the environment is, and this is better to realize and in a more perfect way inside the nucleus.
For somebody like me who would think that atomic clocks are pretty accurate.
Oh, they are, yeah.
So why would we need a nuclear clock?
They are the most accurate measurement devices ever built by humankind. And I also need to admit that when we made this proposal in the early 2000s, since then the atomic clocks that we were also working on made such tremendous progress that a little bit of the advantage that we were seeing for the nuclear clock is gone, because the atomic clocks have also advanced so much. But still there remains an advantage of the nuclear clock in terms of accuracy, stability, and also it's a different kind of clock. And that's interesting, comparing different kinds of clocks in order to investigate physics in a wider sense.
As far as I understand it, it's been quite a long process. So talk us through that, and then what the big breakthrough was. The big
problem was, so we noticed, or it was well established from nuclear spectroscopy, that there would be a very narrow transition. Narrow transition means weak transition, small line widths, as one would like for a clock. But in nuclear spectroscopy, the accuracy of the transition wavelengths was very low. So it was like in the beginning it was only known to maybe 20% or so, and that creates a very bad needle in a haystack problem, like finding a very narrow transition in a very wide search range. The additional complication was that the nucleus, the specific nucleus we are interested in, thorium-229, is radioactive itself. So if you may say, okay, I need to look at a weak process, so I work with a bigger sample, but then the bigger sample is more radioactive. Radioactivity produces also light and background. So these were the challenges. And so over the years, the nuclear physics side improved their measurement accuracies quite significantly. And in 2022 they had reached like a fraction of a nanometer uncertainty, and so that was when we zoomed in with a laser. And the final important ingredients for the breakthrough we had in late 2023 was getting a dedicated laser system together that we had built at PDB with a suitable preparation of the thorium nuclei, which was doping them into a calcium fluoride crystal, which was done by the group of Thorsten Schrumm at the Technical University in Vienna. It was two long-term developments taking several years, and then bringing it together was a key to success.
I've read it as it was the second hand starting to move with your breakthrough with the clock. So how do you realize, where do you go from here?
Yeah, I think it's very exciting, and I notice we get a lot of feedback and interest. So I think it is kind of opening a new field. One may call it nuclear laser spectroscopy. It's the first time that the quite established methods of high precision spectroscopy and laser spectroscopy, well used for atoms, for molecules, can now be applied to a nucleus for the first time, only to this one specific nucleus. But nevertheless, I think it opens a new precision window for nuclear physics. The coupling between atomic and nuclear degrees of freedom is quite interesting. And then, of course, the development for the clocks. So I think for the clocks I mentioned already, it's interesting to have a different kind of clocks, one that is not purely electromagnetic, but also relying on the strong forces inside the nucleus. And this opens a field looking for new physics, like where is maybe violations of Einstein's equivalence principle or so, well tested for the electromagnetic clocks. And here we have a new kind of clocks, and we may use it to see if the established laws of physics in the standard model are also valid, or if we find some deviations.
Fascinating. Well, thank you ever so much indeed for talking to us. We really appreciate it, and lovely to see you here, so thank you.
Thank you.